D6 statics the traffic light. So in this case, I have here a traffic light and two cables. These diagrams are not drawn to scale because we're telling you what the distances are. So this is 30 feet. It's easier to see the diagram when it's not to scale. 30 feet, 30 feet, 1 foot, nice trees, traffic light. And the traffic light is 50 pounds. And it's connected in the center. See, this is like a 60-foot cable, and it's stretching a cable a little bit. Find the tension in the cable. Now, when you do a problem like this, what I like to do is, first of all, I like to sketch it. And teachers will like that they see a little sketch. So if you go ahead and sketch a little traffic light like that, say your poles, say your ground here, you can go like this to emphasize that's the fixed ground. And, if you could go ahead and indicate some distances, that would be nice too, like 30 and 30. It's going to be given in the problem, but teachers like it when you redraw or sketch it. The picture of the problem may be like a photograph or something, but here you just sketch it like this. This is good. And you can label this as 50, pounds here as the traffic light. And the sag here, 1 foot. Okay. Then step 2, what you do is what's called the free body diagram. And the free body diagram, or we can call it the force diagram. In the free body diagram, you take the object or a point and put it at the origin. I'm going to pick this point, like right there. You can pick any point. It's all in equilibrium. Everything's static, all right? So if we do this, and you can, give here a little direction. This is X, and this is Y. Then what's operating on this point, see, is you got an mg going down, which is your 50 pounds, your weight. And then you have these cables that are going like this, where there's two forces, and then there's the angle here. It's an angle, say theta. And we can call this tension, T. The tension's the same everywhere in the cable. If you were to cut it and put a way to measure it there, like a scale, you would find T everywhere. It's taut, nice and taut, no slack. And then what you do for step 3, you want Newton's laws. So you want then that the equations, we'll say the equations. So the equations here, since Newton's law, F equals 0 is a vector, you're going to have all the forces. This means sum up all the forces in the x direction, that has to be 0. Sum up all the forces in the y direction, that has to be 0. So if we do the x direction first, I have T cosine theta is the component in the x direction. See, there's my T, can be thought of as having two components. I like to use a different color here. So the red, see, that's your force in the x direction, and that's the force, say, in the y direction. So I have T cosine theta, but then I have minus a T cosine theta there, and that's 0. Now you might say, and tell me anything. Well, that's because we were clever and we used symmetry to determine that the T's were the same. But suppose we didn't do that. And we call this one T1, and we call this one here T2. Like say we didn't know that, all right? Then we would have T2, that's the one going to the right, cosine theta, minus T1 cosine theta equals 0. And if you divide by the cosine theta, or well, let's go ahead and do that and get T2 minus T1 equals 0, you would get T1 equals T2. So this equation is important. It tells you something. It's just that we were clever because of the symmetry. We saw the 30-30 on each side, and we just wrote down that these t's were equal to the same t. Then if we go with the y equation, that would be t sine of theta, and there's two of them that are going up, two of those, and then minus, notice my plus direction is up, is positive y, and then to the right is positive x. So basically using the summation of the forces with the signs. So this is minus 50 pounds is equal to 0. So that means that 2t sine of theta equals 50. And here we could write down that the t is equal to 50 divided by 2 sine of theta. Or you might just at this stage replace the sine of theta, because you have your triangle here. You have a 1 and you have a 30. Remember the 30 feet and the 1 drop. So the sine, so let's go ahead and do that. I think that might be easier. 2t, the sine is 1 over 30 squared plus 1, this triangle there. So it's 1, the opposite side over the hypotenuse, and that's 1 over the square root of 900 plus 1, 901, and that equals 50. So that means that t is equal to 50 times the square root of 901 divided by 2. This is pretty much 30. With the calculator, I got 30.02. And then when you multiply this out, you get the tension is 750.5 pounds. We could just say 750 pounds. Now, I apologize for the US not using metric, so at least convert it to metric at this point. So times 4.45 newtons over 1 pound, and that's going to give us T is 3,300 newtons.